I felt that before going to conclusions, I should add this one podcast based on a review paper in Nature by Tapio Schneider and team, which takes previous research also by people like Sarah Kang, Isaac Held, and puts it into a energy flux context. I kind of mentioned it before with John Marshall's name. John Marshall uses aqua planet model where land is sunk and the whole planet is made up of water, and then looks for ITCZ dynamics and talks about energy transports and ITCZ location. This is basically going to be zonal mean sense, but starting with the distribution of precipitation, you have this is a long-term mean from satellite data, I think, and showing the winds, of course, southeast northeast trades and the subtropical gyres and monsoonal circulations, which are shown kind of annual averaged week circulation. But you can see we have the clearly defined ITCZ, SPCZ, and the Indian Ocean side of the ITCZ and the monsoon rainfall here. But this is the distribution you get when you do the zonal mean. You have the ITCZ which dominates, but you have the Great Cloud Band as well, and there is hemispheric asymmetry there. But more interesting thing is if you look at the moist static energy flux, which I hope you all know what it is. It's basically CPT plus GZ plus LH Q, so the dry static energy plus the moist part. So you can see that there are advections into the ITCZ region, so the flux divergence is maximum there. So if you look at flux divergence, that's maximum in the SPCZ Great Cloud Band region and the ITCZ across the equator, the minimum on the equator. So the static energy itself is moist static energy flux itself is minimum on the ITCZ, but its divergence is maximum. And the idea was that the ocean is carrying energy across the equator in the Atlantic to compensate for the deep water formation against the temperature gradient, in the sense the southern hemisphere is actually colder than the northern hemisphere, but the atmosphere mechanically forces the ocean in the Atlantic meridional overturning and part of the global conveyor belt to transport energy across. So for equilibrium you need somebody to transport the energy back, and that's what the ITCZ does, and this is why the ITCZ is pulled to the north, as opposed to the arguments that it's by Philander and others that the land distribution makes a difference. Okay, this is just a seasonal migration in the Pacific, which is unfortunately averaged over the whole 160 east to 100 west band. So it combines the different regimes that we looked at, with the cross equatorial pressure gradient being strong and weak, but nonetheless you can see how the convergence works during the summer monsoon. There is strong convergence, strong ITCZ, a lot of rain, whereas in the winter months the situation is different here. Whereas over the Indian Ocean sector there is a clear equatorial crossing happening in the boreal spring months, but the ocean is warm, so you still have convergence and rainfall south of the equator, but there is clear cross-equatorial convergence into the monsoon trough, which then retreats after the monsoon is over. There are lots of debates about these processes, about onset of the monsoon and why this is so dragged so far north and so on, which touched upon a little bit, but we'll come back to that during the monsoon discussion. In a mean sense, we have already seen that the Hadley cell has this upwelling branch where deep convection happens. The divergence happens at the top, and then there is sinking in the subtropics with eddies carrying the flux poleward. And right now, as this caption points out, the asymmetry is such that there is more eddy flux required to go southward, because that depends on the equator to pole temperature gradient and the advection of energy northward by the Atlantic meridional overturning circulation. We have the trade winds, of course, and the ocean upwells and creates its own Hadley cell. So we call that the subtropical cell. So it has upwelling and divergence, sinking and return flow as well. It has multiple cells just like the atmosphere, but this is the main cell. So that's what we talked about before, that if you put the heating asymmetrically, then you are going to create upwelling and zonal asymmetry. So cold temperatures in the east, warm temperatures in the west. In the Pacific, for example, cold tongue and the warm pool, and so on. And the other detail that's kind of fun is that if you look at the atmospheric meridional energy flux and the so-called energy flux equator, you can see that if you zoom, of course there is energy flux towards the poles in both hemispheres, but if you look closely at the atmospheric flux near the equator zoomed in here, you can see that the zero crossing doesn't happen on the equator. So on the equator you have southward energy transport, and the zero crossing happens at some delta latitude, which is, I think, in the current climate at 2.5 degrees. So that's the zonal mean, global zonal mean. So we are still not explaining the regional specificities and the zonal differences in ITCZ, but nonetheless this is a useful construct as a whole. Zonal mean ITCZ is placed to the north because the flux divergence on the equator is not the maximum, it's maximum over here. And if you change the flux, then you can move the ITCZ, which relates to things like El Nino, which change the energy flux in the ocean and in the atmosphere, and global warming, etc. Those are the big questions about what determines the zonal mean meridional position of the ITCZ in terms of this energy construct. Okay, it's kind of cute, and Bill Boos and others, I think, have done more work on actually looking at the zonal variability of the ITCZ and its relation to the energy flux in the atmosphere and ocean. And also Tapio talks about, I think in this paper and another paper, how the energy flux has to be compromised here in terms of the split ITCZ, where the ocean requires upwelling over here, I think during the boreal spring or fall months to make up for the ITCZ being so far north of the equator, and so on. Okay, so that's a very different way of thinking, not really completely contradictory in what this chapter says, but it is a different perspective in the zonal mean. So the two are still obviously coexisting, in the sense if you open up the ITCZ and look at processes of inertial instability, they are real, they are measured, they are observed, they are modeled, so they are important, but that doesn't necessarily still explain the energy flux and the zonal mean position. So they are two parts of the same problem. The zonal mean picture gives you a better way of seeing how high latitude can force the ITCZ during, let's say, ice ages, or global warming can influence the ITCZ and the Hadley cell by warming the tropics and the high latitudes differently, and by changing the equator to pole temperature gradient, for example. Okay, so both are very interesting constructs.